Okay, welcome back. Hopefully you found some stuff, added some stuff to your findings list maybe. Let's just think through this system. First question, what type of system is it? You might, in looking around the mechanical room, depending exactly on what you looked at, you might have actually been tempted to think it's a variable volume system. Because there's what appears to be a variable speed drive. And that wouldn't be a bad assumption, but to know it for sure, you'd have to know a little bit about the system. You'd have to know what the terminal control equipment's like. And this model isn't actually developed far enough to show the terminal equipment, but if you may or may not have noticed, the operating team down on the wall near the discharge end of the air handling unit, they actually have a system diagram mounted. A lot of operating teams do that. They have a system diagram on the wall for the operators to reference if they need to when they're working on the building or working on the system. Sometimes they even have the control drawings. And so if you look at the system diagram, basically, there's a supply fan, which is at the end of the unit. So basically, this is the stuff that's in the mechanical room. And here's the ballroom. It's a large ballroom with a folding divider, is what that note says. And there's 2 hot water reheat coils with manual balancing dampers, but there's no volume control equipment. So unless there's been a retrofit of some sort since this drawing was hung on the wall, which is a possibility, unless that a retrofit has happened, then basically this is configured to be a constant volume system. In other words, there's nothing to vary the volume. It's a reheat system. It's got an economizer, it's got a preheat coil, and it's got a chilled water coil. So there's the answer to the first question. It's a constant volume reheat system. And right there is an opportunity. Okay? And I'll leave you to ponder that. We'll actually come back and talk about that in a different webinar. But I'll leave that to you to ponder. What is the opportunity? And the opportunity actually is a way to take something that's actually an energy penalty now and use it to our advantage that would save energy on a number of fronts. Okay, it would save fan energy and it would save HVAC process energy for a number of different processes, and it would leverage something that's already here that's not being used to its best benefit. Okay, second question was what's the function of the dampers on the wall in the mechanical room? Went too far there. In other words, if you step back from just a little bit more, there's some dampers on the wall that go to the outside. Well, you might think, well, they could be outdoor air intake dampers, and this would make the mechanical room an outdoor air intake plenum. But that kind of doesn't make sense, because if you remember this duct, if you follow this duct and go back to the overview, that duct goes to this louver, which is also an outside air louver. And so if you follow that duct back to the view that we were in a minute ago, it comes into the back end of the unit. I've got the doors open right now. But it comes into the back end of the unit, and the airflow basically is from this end of the unit towards the supply fan. So that's probably the actual outdoor air connection. These dampers here, if you look closely, basically feed air into a place where the outdoor air comes in, and there's a damper there. So this is probably the economizer section, the mixed air plenum, which would make these the return dampers, which would mean this is a return air shaft. Clearly this is a supply duct coming off the fan. So this is a return air shaft, and the rooms of the mechanical rooms are return air plenum, and so the dampers on the wall are the relief system. Okay. And so one thing you might ask yourself is, should those dampers be wide open or not? Right now they are. Relief air basically is air that you have to leave out of the building that you brought in to provide free cooling in the economizer process. So aside from leakage, the relief dampers ought to, in some ways, track what the outside air dampers are doing, especially on a constant volume system. So if the relief dampers are wide open, you'd expect that to be happening because the outside air dampers are wide open. But if we go back here and take a look, and we can sort of do it as if we were looking in a door here. Clearly the outdoor air dampers aren't wide open. So we have something else to put on our finding list, right? So this is AHU2. Relief dampers may not be functioning properly. They're wide open with the unit not on 100% outdoor air. And so right now we don't know if that's worth any money, or if it's an indoor air quality problem, or what it represents, but we do know it's something that doesn't appear to be right. So we want to make a note of it and follow up on it later. So now this actually begs the question in a way, well, given what you know about what's going on outside, would you have expected this unit to be on minimum outdoor air? It looks like it's not on 100% outdoor air. Or would you have expected the unit to be using 100% outdoor air? The things that we know, if you remember the equipment room or the equipment schedule back in the central plant when we were looking at it, here we can just pop back there and take a quick look actually. So this is the ballroom air handling system right there, the main ballroom. Its design leaving air temperature is 51.4 degrees. Okay. If we look, at our remote transmitter, which is actually information coming from the control system on the air handler we're looking at, it's 52.2 degrees outside. In other words, the outdoor air temperature is pretty close to the leaving air temperature. And so you'd think, well, gosh, why wouldn't you just use the outdoor air? And you'd sort of expect that in a way, but the one caveat, and one thing to remember is when we came on the site, remember, it was foggy, which means the relative humidity is about 100% outside. So humid air that's cool may have more energy content than warmer, may have more energy content than humid air that isn't saturated. The only way you can really know the right answer to this is to look at the situation on a psychrometric chart. The good news there is you can actually get a really nice psych chart for free, an electronic psych chart. If you go to my blog and basically type in psych chart, I'm actually teaching how to build one as a build code trick. It's kind of a nerdy, very cool thing actually. But this link right here takes you to a blog post. This blog post will link you up to the download of the free version. It'll walk you through how to use it, how to plot some basic points and stuff like that. And then it'll show you how you can use it to plot processes, even though you can't directly do it in the chart. You can take the image and do it the old-fashioned way like we used to. We'd draw on it. And you draw on it in PowerPoint. And it walks you through how to do that. But then it also shows you some of the features you would get if you were to upgrade this psych chart to the professional version. So having said that, I'm going to go ahead and open up my copy of the professional version, and let's think this through. Okay, so what do we know? Well, we know that outside it's what temperature was it outside? Let's go back. We have a outside air temperature transmitter on this unit. Right back here. This is actually where the signal in the central plant's coming from. It's a retransmit off this device. So it's 52.2 outside. Okay. And to plot a point on the cycle chart, you need to know both a temperature and some moisture condition. And since it's foggy, that lets us imply that the moisture condition is 100% relative humidity. Now, if it was raining, that wouldn't necessarily be true, because when it's raining, there's actually some the water's evaporating, which actually desaturates the air a little bit, because to evaporate it takes some energy. And so when it's raining, it may not be, it'll be really close, but it may not be saturated. But if it's raining and foggy, that means there's condensed water floating around in the air. It's definitely saturated. So we can plot a point that represents the outdoor air conditions. And so if you're doing this in the Pro version, you'd say add a point, you'd say outdoor air. And in the Pro version, you can make it, different colors. So let's maybe make it blue. And so it's, the temperature is 52.2. 52.2, and the relative humidity is 100%. And then say apply. So there's the outdoor air condition. Okay. So now the question becomes, what's the indoor condition? And the one thing we have going for us, though, is in most buildings, the air that's in the building, and therefore the moisture that's in the building as a baseline, came from outside. So the specific humidity of the air in the building, in other words, the pounds of moisture per pound of dry air, has to be at least the same as the outdoor air condition, unless there's a desiccant manufacturer's convention going on and they have all their desiccants out for display. And it's probably a little higher, because there are other things in the building that add moisture, like people, for instance, and cooking processes. But if we just made a simplifying assumption and said, well, we're going to assume the specific humidity in the building, the pounds of moisture per pound of dry air, or grains of moisture per pound of dry air. We can talk about what grains means and why we'd use that, but it goes back to the slide rule days. We're going to assume that's the same as it is outside. And we're going to assume that the temperature in the building is basically at or around the standard this hotel has for their ballrooms, which is 72 degrees Fahrenheit. So to figure out what the outdoor air specific humidity is, there's actually a number of ways we could do that. One is, you'll notice if you watch over here, as I move this cursor around the chart, it's telling me the values under the cursor. So if I hover the cursor right over that point and look at what W is, that's the symbol for specific humidity. It's about 58.2 grains per pound. So that's one way I could do it. Another way to do it is, if you're building this table, as soon as you entered the two parameters for your point, all the other parameters for that point show up here below it, and they also show up in this table. And there we can again read that the specific humidity is 58.2. So let's add a second point. So this will be the space condition. And the space condition is, we're going to assume it's 72, and we're going to assume the specific humidity is the same as the outdoor air. So specific humidity is what was it? W, 58.2 grains of moisture per pound of dry air. So there's where a space condition probably is. It could even be a little up this way because of the moisture. Now the space condition may or may not be the return condition. There's a lot, sometimes there's, not sometimes, most of the time there's heat gains in the return, if for no other reason than the light fixtures are sticking up into the return plenum a lot of times, and so some of the heat from the light ends up in the return air. If there's a roof load, that'll end up in the return air. And in fact, if we go look at what's going on with this air handling unit, oops. If we look at the return section, if our sensor's right, it's about 73 degrees in the return air, 73.4 to be specific. And so let's add that point on our psych chart, okay? And so the air starts at the space and it flows through a duct to the return of the unit, and it picks up a degree or so of heat. So let's see here, go back to my point chart. So I'm going to add another point. Call it return air. And it's unlikely that any moisture got added in the return air stream. So we're going to make that same assumption, that the specific humidity of the return air is the same as the specific humidity in the space. And plot that point on that basis. And so we're going to say the temperature in the return is the temperature we're reading here, 73.4. And the specific humidity, we're going to say again, is 58.2. And let's make that orange or something. And let's put the label below and to the right. Now, as an aside, there's actually a way we could have figured out about how much moisture was added to the air by the people in the building. For the time being, I'm not going to go into that, just to keep things moving here and not get too far off in the weeds. But basically, what that means is there's our return condition, okay? And basically, the decision about whether we want to use outdoor air or return air in a cooling process, it comes down to what's the energy difference. In other words, you want to cool the air that has the least amount of energy. And so I'm going to zoom in on this a little bit so you can see it a little better. And the way we measure the energy of the air is by this enthalpy parameter. Enthalpy sounds sort of scary and woo, but it just is a word that means internal energy, and of H equals U plus PV, internal energy and flow work. We really don't need to get in that, but for the purposes of our discussion, if you know the enthalpy of the air, you know the energy content, both in terms of the sensible energy and the latent energy, the energy that's keeping the water in a vapor state. And so if you can read the enthalpy just by, there's a number of ways you can do that. You could open up our little table, and the symbol for enthalpy is H, and the enthalpy of the outdoor air is 21.55. The enthalpy of the return air is 26.71. So the return air has more energy in it than the outdoor air, so we would actually want to be on 100% outdoor air under the current condition, even though it's foggy outside. That's sort of misleading because we think of relative humidity, but when you're working with HVAC, you really need to think of specific humidity. And what I mean by that is, if I could magically take a cubic foot of that foggy outdoor air and bring it into the building and let it warm up without letting mass transfer to or from that cubic foot. In other words, energy could get in and warm it up, but mass couldn't. Basically, you would move horizontally across the psych chart, right? Because a psychrometric process that only had sensible energy is a horizontal line on the psych chart, be it a constant specific humidity, a constant dew point. In fact, let's add a constant line. So we're going to add a constant humidity ratio line, and we're going to reference that to the outdoor air condition. We'll make the line blue, give it some weight, say apply, and there you can see that's exactly what we did in our analysis. We assumed a constant specific humidity. Notice that didn't change, and so that magic cubic foot that we brought in, the fog had dissipated as a sensible energy as the temperature increased its sensible energy, because now you have more energy for the water molecules and they can break free of each other and go back into the vapor state. But the pounds of water per pound of dry air didn't change because we constrained it, right? We said we got this magic cube that heat can get through, but mass can't get through. Well, if the pounds of water per pound of dry air didn't change, we moved horizontally across the chart, and the relative humidity went from 100% to in the range of 50%. Okay? So that's why it's useful to think of humidity as specific humidity or humidity ratio or dew point when you're working on HVAC. That's what we're really worried about. So we've got another finding for our finding list, right? I'm going to save this so you can have a copy of it. Basically, it appears that the Economizer Interlock isn't working. Economizer dampers appear to be stuck on minimum outdoor air when they should actually be allowing 100% outdoor air, assuming an integrated economizer. Okay, if it was a non-integrated economizer, it might actually do that, but then that would sort of say, well, there's an opportunity anyway. And if you aren't familiar with the difference between an integrated and a non-integrated economizer, we'll eventually get to that, but Brian may have already talked about that. Okay, so now our findings list is growing, right? And if you think about that, so if we could cool, achieve the discharge temperature set point by using outdoor air, there's some of that load on the chiller plant that shouldn't be there, right? Because right now we're basically mixing we're mixing a whole lot of 73.4 degree air, right? This damper is virtually wide open. Mixing a whole lot of 73.4 degree air with not very much. You can't really assess airflow just by the position of the damper if it's not well sized. But clearly this isn't wide open, so there's probably more return air than outdoor air, so the mixed air temperature probably is closer to the 73 number than not. And in fact, here's a sensor right here. It turns out that's the mixed air sensor, right? Yeah, and it says that the mixed air temperature is 70.8, when in fact, so we're basically, it looks like so far, taking 70.8 degree air and cooling it down to 52 degrees with chilled water. That's an unnecessary load. So there's part of the mystery load on our chilled water plant. So I'm going to go ahead and bring this part of the module to a close. And there are a number of other things going on in this mechanical room. And so in the next module, we'll take a look at a few more of those things before we head back to the central plant and look for some other opportunities there. So once you've digested this, again, you may want to try to recreate this on your own, sort of walk through the reasoning, get a psych chart out, see if you can plot those points. But once you feel sort of comfortable with it, go ahead and open up the next module and we'll pick up in this mechanical room where we're leaving off right now. Meanwhile, I hope you have a nice rest of your day, and I'll look forward to seeing you virtually, I guess, in the next module. Thanks much.